Hey, how's it going? Figured we'd make a new slide today, our first one, and we'll go ahead and talk about Equilibrant. Alright, so I figured I'd get dressed up for this one, that way I don't look too sloppy. Where's my marker? But yeah, before we start, let's just go ahead and talk about what Equilibrant is. The formal definition of it is a single force vector. Remember, a vector is anything with magnitude and direction that you introduce into a situation that will bring the object to an equilibrium state. So what the heck does that really mean? Well, I'm sure you're not going to tell it to your friends whenever they ask you what it means. You'll probably say something like, well, it's a force vector that we introduce to cancel out any unbalanced forces. So if an object is moving, what vector and in what direction, how big must it be and in what direction must it be in to bring this object to a stop? Also, if it is moving and there is any unbalanced forces on it, what vector can you put in to cancel out any unbalanced forces acting on the object? Just what will bring the net force of the object to zero. So, here we go. Oh, there it is. Alright, here are some equilibrium examples. Let me switch to pen. And here we go, pen is now here. For example, first example is this. Example number 1. Sorry for my handwriting. I need to get better at this bamboo. Let's say I have a dog bone. There's a bone. The dog is pulling with 3 newtons to the east. You are pulling with 5 newtons to the west. First question is it in equilibrium? Equilibrium. Is it in equilibrium? Let's see, you've got 5 newtons to the west, 3 newtons to the east. Will those cancel each other out? The answer is no, they will not. So it is not in equilibrium. And what direction is it moving in? How much force is it moving in that direction? The answer is it is moving to the west at 2 newtons. Alright? So it's not in equilibrium. It's moving to the west at 2 newtons. So the next thing we want to figure out is what could be the equilibriant? Remember, what was an equilibriant again? It was a single vector that you introduce to a problem that will bring this situation to a balanced state, that will cancel out this vector. So let's see. You've got 5 pulling to the west. 5 newtons, I'm sorry. You've got 3 newtons pulling to the east. What should we put here? What should be another single vector that we can add to cancel this 5 out? Well, we know it's going to pull with 2 newtons to the west, so we need 2 more newtons going in the opposite direction, which would be to the east. So now let's see. You've got 5 newtons to the to the west. You've got 3 plus 2, that's 5 newtons to the east. Well, what happened with this 5 to the east and this 5 to the west? Great job. They will cancel out. So our equilibriant is going to be, ooh, I wrote a 5. Let me erase that. No, I don't. Sorry. Please bear with me. There we go. Yay, it's erased. Pen. Our equilibriant will be 2 newtons to the east. There you have it. Look. It's a single vector helping this bone stay balanced. So now the dog is not being pulled by you. Now you and the dog are still struggling for this bone. What if we did this? What if we said, there's your 5 newtons, same situation, there's the bone. There's your 3 newtons. What if instead of having the 2 newtons, what if we decided to do this? 1 newton to the east, plus another 1 newton to the east. Can we now say that these are equilibriant vectors? The answer is no. You cannot do this. Because the definition of an equilibriant is it is a single force vector. Keyword there is single. This is 2 lines. You cannot do this. So good. Next thing. What if we had this? Here's an object. It's got a force applied to it going in the north direction at, let's say, 12 newtons. It has another force being applied to the east of it at 12 newtons as well. Sorry, this is example 2. Alright, these two forces are acting on this object. Is this object in equilibrium? Let me change the pen color. Let's go with this blue. Alright, is this in equilibrium? Equilibrium. That's the first question. What do you think? Here's 12 pulling, here's 12 pulling. What's the definition on vectors? If they're going in the same direction, what do you do with them? You add them. If they're going in opposite directions, what do you do with them? Subtract them. So are these guys going in the same direction? Let's see, he's going north, he's going east. No, they're not going in the same direction, so we will not add them. Well, maybe they're going in opposite directions. He's going north, he's going east. Last time I checked, south was the opposite of north. So they're not going in opposite directions. These are going in different directions. Since they are going in different directions, we cannot subtract them, we cannot add them. So if you're going to do something, you will do the Pythagorean theorem to them, but we're not there yet. So the question we were asking is it an equilibrium? The answer is no, it is not an equilibrium. If he pulls up and he pulls east, this object is going to move right here in the middle. It'll move in this direction. So the answer is no, it is not an equilibrium. Now the next question is, well then, what could be the equilibriant? Well, to have an equilibriant, you've got to know the size and direction, right? So let's see, we can assume, well, first thing is, let's figure out the size. How much force do we have to pull to balance this stuff, to balance this pulling? Do you remember from our old vectors where we did this? We went this direction. Let's give it 12, and then let's scoot him up 12. All I did was I just rearranged this vector and this vector. I just rearranged them. I wrote them over here. Now, to find out how much force they're actually pulling with, you've got to find this displacement right here, your resultant. So remember how to find it. If you don't, no big deal. Here we go. You do the square root of 12 squared plus the other side, 12 squared. And put that in the calculator. Oops, I didn't grab one. Let me grab one real quick. Be right back. Yay, I'm back. Alright, let's see. Square root of 12 squared plus 12 squared is 16.97. So, the resultant force that it's pulling with is 16.97. Let's just call it 17 for the sake of this example. 17 newtons. So that means it's being pulled in this direction with a force of 17 newtons. Do you agree? Alright, next thing. If I want to offset that, our equilibrium is going to cancel that out. So we want to cancel out this movement of 17 newtons in this direction, which is the northeast direction. Which way should I go? By the way, it says 12 newtons northeast. Oh, no it's not. That 17 is 17 newtons northeast. So what's the opposite of north? South. What's the opposite of east? West. So we'll be going in this direction. With how much force do we need to go to? Exactly. 17 newtons. So here's what it will look like. At the end of this drawing, you have your 12 newtons, your other 12 newtons, and your equilibriant is that, 17 newtons. That, my friends, is your answer. And 17 newtons southwest is your official answer for your equilibriant. That's it. It's about as hard as it gets. Let's go ahead and do this next scenario. What if you have this? They may also give you something like this. Can the following forces be at equilibrium? Can the following forces be at equilibrium? Oh, yes. Let's see. Scenario 1. Let's say I give you, give me 3 numbers. Good. Give me another one. I like that one. Another one. That's a weird number, but cool. I'll use it. Let's say we have 3, 5, 17. We don't know what direction they're in. We don't know anything. We don't know if it's pulling north, east, west. We don't know. But the question is, can we somehow arrange these 3 forces to where the object will be at equilibrium? What does equilibrium mean again? Balanced. There's no uneven forces on it. Your net force will be 0. So let's see. To figure that out, here's what you do. Pick any 2. Which ones do you want to pick? 5 and 3? Perfect. 5 and 3. First thing we'll do with them is we will add them together. So you end up having 5 plus 3. What do you get? Great job, 8. Y'all are super smart. Next thing we'll do is we will subtract the 5 and the 3. What do you get there? 2. Ooh, look at you. Great job. So you get 5 plus 3 is 8. 5 subtract 3 is 2. If for some reason you write 3 subtract 5 and you get a negative 2, just ignore the negative 2. Just leave it as positive 2. Leave these numbers positive for now. We want the absolute value of these numbers. That's the algebra 2 reference for your absolute value. Alright, so we have 8 and 2. This is our range. We can have an answer as low as 2 or an answer as high as 8. Or anything in between these. So let's see. We used the 5 and we used the 3. Who do we not use? We did not use the 17. Is the 17 in the range? No, it's not good. It's too big. So the answer is no. It will not work. It will not work. They cannot be at equilibrium. Well, what if we picked another 2 numbers? Let's say we pick 3 and 17. Here's 3 plus 17, 3 minus 17. This is 20. This is 14. It's actually negative 14, but we don't care about the negative right now. That's our range. We use the 3, we use the 17. Who do we not use? The 5. Trying to see if they'll get to a 5. Is 5 in the range here? Is it as low? No, it's not. So it won't work there either. The last time, let's say we use 5 and 17. If we add them together, we get 22. We subtract them, we get 12. Let's see, the number we're missing was 3. Does that work? No, it does not work. So the answer is no. So in future references, you don't have to really test all 3 scenarios. You just pick one, test it. If it works for that one, then it works for all of them. If it doesn't work for that one, then it will not work for all of them. Let's try this other scenario. Let's say the numbers they gave us were, pick another number. 11. Cool. Pick another number. 4. Sweet. Pick another number. 9. Let's see if these work. Let's pick 4 and 9. Those are the smaller numbers. I got the 4 plus 9. What do we get? 13. 4 minus 9. What do we get? Negative 5. That's true. It is a negative 5. But we just want the positive values for it. This is our range. The number we left out was the 11. Will the 11 fit in this range? Oh, wait, it's not 5, it's not 13. Yes, it is smaller than 13. It's good, it will fit. So yay, these will work. If for some reason when you do your math, let's say this number was actually a 13. If that was 13, would it still be in the range? Yes, it would. You could still count it. And you're good. That's pretty much it for Equilibrium. In Equilibrium, y'all have a wonderful day and get to work and go read a book or something. Just kidding. Alright, we'll see you later. Be safe. If I could figure out how to stop this.